Okay, so thanks everyone for coming nice and early on day 3, which was not easy, at least for me, so probably not easy for everyone else either. So what I want to talk about is the Sim Foundation's effort to formally verify zkEVMs and the EVM that would run on top of zkEVMs. You've probably heard about zkEVMs recently because there's been a lot of noise about them, with a lot of companies reaching some level of maturity, like RISC-0, Succinct, Jolt is kind of getting there, Zisk and Powder, OpenVM, and many others. And we have a kind of big list here, about 20-ish zkEVMs. And if you don't know what a zkEVM is, a zkEVM is this kind of nice general purpose virtual machine where you can take any program that you can compile to that zkEVM, which is sometimes a bit of a caveat, and you can generate some cryptographic proof of its execution or some other property of the program once you do that. The nice thing is that this means you don't need to write a circuit for your specific program, and so it's an attempt to kind of commoditize verifiable computation. This is quite attractive. Obviously, it removes the need for a lot of apps who might want verifiable computation to have in-house cryptographers to write these circuits. And as we all know, obviously, writing circuits that are not under constraint or just in general secure can be a bit of a challenge. So the more we can make that something that doesn't have to be repeated all the time, that seems kind of nice. You'll see a couple patterns if you look at the list of zkEVMs. One of these is RISC-V, which shows up as the most common underlying ISA for the zkEVM. And the other one is Rust, which shows up as the most common front end for a lot of zkEVMs. And both of these will come up a bit in what I'm going to say when it comes to actually formally verifying zkEVMs and programs that would run on them. So with respect to Ethereum in particular, we actually have quite a few plans to embed zkEVMs within Ethereum, and that includes for the consensus layer. So you can go and see Justin's Beamchain talk at DEF CON. The idea there is that instead of the consensus layer working as it does now, you would instead actually have zkEVMs used to prove the state transition function. And this would be using some combination of multiple zkEVMs. If you look at the slide there, you had RISC-0, Succinct, Jolt, Powder, Nexus, Scroll, and the zkSync zkEVM listed. And if you've seen this list before, that list of potential zkEVMs that we could use has grown quite a bit. We also have native rollups, which are coming up. This is a bit more recent than DEF CON, but the idea with native rollups is to do what feels like to me rollups should have been from the start. But here you would basically be able to expose some kind of execute precompile at the EVM level, and therefore allow rollups to kind of get much closer to the layer 1 execution layer. And again, we would use zkEVMs down the road to actually prove the execution of whatever rollups are doing, instead of having to go through re-execution and the downsides that comes with in terms of scalability. And it's also somewhat reminiscent if you have things like Arbitrum Stylus, and people have been exploring this idea of kind of alternative VMs to be able to execute a wider range of programs. And we've also been thinking about exposing RISC-V as a lower level VM than the EVM, which would give us a bit more flexibility, particularly with respect to rollups that might have state transition functions that are different to the layer 1 EVM state transition function. Performance of these zkEVMs is only getting better. We have a nice new website that's been set up by other people in the Foundation called easeproofs.org. You can see some benchmarks here in terms of the time that it takes to prove an EVM block, as well as the cost. All of these benchmarks are on kind of single machine AWS provers. If you do want to scale this down to something that gets close to real-time proving, I think proving all EVM blocks for a year in under 30 seconds per block would be in the range of maybe 150K, 200K, something of that order of magnitude. And then if you wanted real-time proving, which would be less than 12 seconds, or in the context of the beam chain, maybe less than 4 seconds, you would add some number to that. But between kind of hardware improvements, as well as improvements in terms of the proof systems and zkEVM design and engineering, we are getting fairly close to making kind of real-time proving somewhat realistic and affordable for us to use within Ethereum, and presumably a lot of other applications as well. So because we're planning to use zkEVMs quite heavily, they're also going to become security critical. It's obvious that if you have issues in anything zk, things can blow up fairly quickly. And for that reason, the EF is investing essentially $20 million over the next 2 years, starting a few months ago, to make sure that we can set everything up to formally verify them, but also to develop all the tooling that's required to keep them formally verified down the road, because we expect things to keep changing, both in terms of engineering, but also in terms of the proof systems. And so we're running this big program which has a lot of grants and a lot of bounties available, and I'll talk a bit about some of the work that's already ongoing and some of the work that's coming up in the future. So we split our kind of task into 3 tracks. The first is the zkEVM track. This one is somewhat self-explanatory. You're looking at the zkEVM. One big thing is obviously the circuit that actually is meant to implement or encode RISC-V semantics into it, or add some other ISO semantics if you're using another ISO. You'd want to make sure that that circuit is, actually correct, in some sense, sound and complete. Certainly, if you think of it optimization, and if you're thinking of it in circuit terms, at least not under-constrained and not over-constrained. And I'll talk a bit more about this in a second, but essentially you want to make sure that if you are going to get a proof, it's only for a valid computation. You've got the EVM track. This one I think is also fairly straightforward. We have many implementations of the EVM, maybe only one in Rust so far that runs on zkEVMs, but we expect that to expand in the future. And the key thing is to make sure that if we are going to have formally verified zkEVMs on which an EVM is running, that we also have EVMs that are bug-free. And for that, we'll be basically checking that if you take an EVM and you compile it to a zkEVM, most likely a RISC-V zkEVM, then that compiled EVM actually matches the behavior of a formal EVM specification, and we're fairly lucky to have a couple EVM specifications that we can already use. And then the last track is about cryptography. The zk part, or succinct, if not zk, of zkEVMs is that you have a proof system that has to run on top of them. Proof systems have been changing quite a bit. There's been obviously a lot of people working on new proof systems all the time, and we want to make sure that if you're building a zkEVM, you can switch to a new proof system without too much worry about security. And for us, this means developing executable specifications of proof systems that are formally verified, in the sense that they're directly tied to a security proof for the expected security parameter, and then making sure that we can verify actual implementations in Rust of these proof systems against our executable specifications. So to get into a bit more detail about this, with the zkEVM track, we're working off of the reference cell RISC-V specification. We recently had a grant that's made a lot of progress towards adding a backend to Sail, which is a language for defining ISAs. And this means we can extract the reference RISC-V specifications to Lean, and we already have extractions that existed before to Rock, Hawthorne, and Isabel. So the specification for RISC-V is actually ends up being quite big. I think the Lean spec at the moment is about 100,000 lines of code. We'll do a bit of massaging to try to put that into a proof for a circuit that's meant to encode this. But we are aiming to kind of go from something that feels like the best ground truth possible, and that would be the reference RISC-V specification. And then when it comes to actually looking at the circuit, we've got a couple of approaches, and I think here we're trying a few approaches from the start, and we'll streamline things as we go along. So for things like Jolt or Plonky3, which are already used by zkEVMs that are fairly well developed, Plonky3 in particular is, I think by far the most widely used implementation of a proof system that zkEVMs rely on. We'll be just developing extractions for these 2 proof assistants, whether that's Rock or Lean. And you'll hear a bit about the extraction from Jolt to Lean in a bit later today from James. But these are very nice. We can get the circuits into proof system. We can verify properties of these circuits. But down the road, because people are writing circuits in many, many different DSLs, and people are probably going to keep coming up with many, many other DSLs, we are also going to try other less kind of naive ways of doing things. One of these is to just write circuits directly in Lean. We have a bit of experimentation going on with this, with zk security in particular. I see some thumbs up, which is always good. This is actually quite interesting. You can, Lean in particular is just quite a nice functional programming language, so it's not that bad to just try to write, kind of reasonable code in it. And the nice thing is then you can just prove your circuit as you write it, and you can get it to a point where you have these nice generic composition theorems, where if you have completeness and soundness that's been shown for a subcircuit, you can get a proof of completeness and soundness for an entire circuit composed of sound and complete subcircuits. We started this fairly recently. with, as I said, zk Security, who have some in-house expertise on both looking at a lot of circuits as part of their security work, but also some in-house expertise of actually coming up with circuit DSLs. And Greg in particular, I think, wrote a TypeScript-based circuit DSL when he was working at O1 Labs. The nice thing here, it also means that because you're proving things as you go along and you have a proof that's directly tied to your circuit, when you want to add an optimization to your circuit manually, you can verify that it doesn't break your proof or repair the proof accordingly. And so you can also optimize further or with a lot more confidence than if you're just trying to do manual optimizations on some Rust code or some Circom code or some other kind of DSL code, where you're really just kind of hoping for the best and trying to reason maybe on pen and paper, or maybe not even on pen and paper, about the correctness of what you're doing. The interesting thing here is to figure out, can we write circuits in a proof assistant and have these circuits actually be performant? One way to do this is maybe to just kind of, extract a description of the circuit to Rust in a faster language, and we'll be playing a bit around with this in the future. And we'll also try to work from what we have now, which at the moment is a kind of prototype proof of concept of a Kachak precompile, which has a fairly surprisingly nice proof attached to it, but we'll try to obviously build this up to some kind of VM or subset of RISC-V circuit in a few months. Now, the other approach that we can try, which is to mainly deal with the fact that people are using many, many DSLs and kind of come up with many, many more other DSLs, is to actually just develop a nice IR for circuits. This has been tried before. There's always a risk of just adding another IR to the stack that people are not necessarily going to choose. But we are actually doing this. So with Veridies in particular, they've been developing an MLIR dialect for circuits that should provide a nice unified layer to work from in terms of verification, as well as not just verification, but verified and automatic optimization passes and things of that kind. That MLR dialect will be open source in about a month, and then we'll be building up tooling around it. The initial integration with a high-level language will be with Zergin, because Zergin has its own links to MLIR, which makes it easy, but we'll be expanding the integration to that as much as we can, and hopefully it means that if someone then later on decides to do a new circuit DSL, from the start they can think about compiling down to that MLR dialect and benefiting from all the tooling that will be going on around this, which should be, hopefully should work well, and hopefully it enables people to write circuits in an easier way because they don't need to optimize them by hand as much, benefiting from whatever optimization passes we develop at that IR level. But also it allows us to embed with a lot of efforts that are going on with verifying MLR dialect semantics in proof assistants like Lean, which is also doable in Rock. And we'll be developing extractions from that dialect to Lean and Rock with the aim that we can apply a lot of SMT solver-based tooling at the MLR dialect level directly, but if we can also extract them to proof assistants, any proof obligations that we can't do with SMTs, we can then verify manually in a proof assistant. The other thing that's very much on our mind, and it is somewhat, maybe not trivial, but feels like it should be doable, is to just try and develop kind of general purpose proof infrastructure for circuits. And this means figuring out how to represent circuits in a nice way, figuring out good tactics in proof of systems to prove things about circuits, particularly when it comes to things like modular arithmetic and other kind of manipulations of integers, or finite field elements rather. And in particular, something that's come up with circuits a lot, which has been actually quite helpful in terms of verifying circuits, is the use of lookups. The nice thing here, especially if you look at the dual circuits, you don't have a lot of gates, you just have lookups for every instruction. You can think about just formally verifying the lookups themselves, and then you can kind of probably compose proofs for circuits from the proofs that you have for the lookups themselves. And that seems quite attractive because you manage to get something that, one, obviously you get much simpler circuits. The difference in circuits for different arithmetizations when you're only using lookups become much lesser. You can kind of squint at an air circuit that just does lookups and an R1 CS circuit that just does lookups, and they don't look as different as they do for maybe some of the older kind of circuits that were just a ton of gates. And if you could then compose proofs from formalizations of the lookup arguments, maybe things become a lot more easy to deal with. Now, for the EVM track, so we're very lucky to have existing formal specs for the EVM. We've got some in K, developed by Runtime Verification, which was the first ones to actually develop formal specification of the EVM, or formal semantics. We've got one in Lean, developed by Nethermind, which I think as of recently is the one that passes the most conformance tests, so shout out to them. And then we've got one in ACL2 developed by Kestrel, and one in Hall 4 developed by Ethereum. which are both somewhat work in progress, but it wouldn't be too much effort to bring them up to date as soon as we need to use them. The goal of using these specifications is to be able to verify implementations of the EVM against these, and we're already doing this now with REVM. So REVM is the kind of canonical Rust implementation of the EVM, at least until maybe Lambda class finish up their work on LEVM. And so this means that because RISC-V zkEVMs primarily use Rust as a front end, this is the EVM implementation that every zkEVM uses at the moment. So we're already verifying this against KVM. This is done in collaboration with runtime verification. And we're also then developing a lean backend for K, which will allow us to make sure that the lean specification of the EVM and the K specification of the EVM are actually equivalent, as a nice sanity check that we haven't messed up the specs. Or at least if we've messed them up in the same way independently, and that would be interesting to find out as well. We're also in collaboration with Baz and Carl Palmskog, who is at KTH, Baz is at our house, developing a canonical ROC implementation of the EVM. And the idea there is not just to have a formal spec, but to have an actual fully fledged implementation that can be used, can be performant, and can be compiled via a certified computation pipeline, which will then save us the trouble of having to verify an actual implementation against it. This would also include precompiles, using the fact that ROC obviously is well equipped to do all of that, and we'll have more updates about this in a couple months. The big question here for us, I think, is maybe not so much how to verify EVM implementations. To some extent, it's somewhat, standard program verification up to the amount of work that it requires. What we're really thinking about is how do we deal with the fact that obviously we have many more EVM implementations that need to be verified, even if we're thinking about things like client diversity. That might become less important as implementations of EVM get formally verified, but they still remain important just to maintain maybe some diversity in the software stack, and to prevent anything kind of blowing up, because there are always some small caveats to formal verification, as well as just allowing people to use something they don't want to use, but to explore different ways of implementing the EVM, which is something that helps push performance in the long run. So verifying other implementations of EVM partially depends on just zkEVMs adopting other implementations of the EVM, and thinking especially with respect to applying zkEVMs to the Beam chain. There we have obviously kind of clients in Go, C#, Java, Zig, whatever people will develop. And so at some point, we'll get around to verifying more implementations, and that'll be also using the fact that we have multiple other specifications and therefore teams that can do this kind of work in parallel without becoming a big bottleneck. Now, with respect to cryptography, I'll actually talk a bit more in detail about this in about 10 minutes or so. We're combining two talks where I'll talk a bit about zkLib. But the main thing that we're developing at the moment is zkLib. This is a lean library of executable implementations of proof systems, or executable specifications of proof systems, rather, that will be directly tied to proofs in lean for those proof systems. This is fairly early days. We recently had a complete proof pass for a one-round sum-check protocol. Most of that involved actually just fixing things in terms of the infrastructure. And from this, we've learned a few more things to fix, but we'll be expanding this up to handling more proof systems. And we will be doing Spartan, Friester, over the next couple months, and kind of growing that endlessly. And we're very much looking forward to having the library in a state where we're not making breaking changes anymore, and where people can start contributing kind of whatever proof system they would like down the road. This doesn't have to be proof systems that are specific to the Ethereum ecosystem. Any kind of IOP should be implementable within this library. And yeah, there'll be a few more details about this in about 10 minutes time. But the next thing, once we have proof systems that are actually implemented in zkLib, will be to actually verify implementations of these proof systems, most likely written in Rust against zkLib. And here we'll be looking at tooling like Hicks or Anus that have been developed independently for kind of Rust verification and linking Rust to proof assistance. Now, there are a couple challenges to everything that we're doing. Unsurprisingly, I think everyone has a sense that formal verification is fairly well known as being hard. One big challenge on top of formal verification being hard is that zkEVMs are incredibly complex. They're fairly new technology, which means that also they're changing fairly rapidly. There are a lot of design decisions that you can make in terms of how modular you are or how unmodular you are. RISC-V, as a spec, is fairly modular. So there's accommodating the fact that people might use different RISC-V extensions, even if for the moment maybe the only split is between kind of using a 32-bit or 64-bit RISC-V implementation. And there's a lot of zkVMs, right? So when we're talking about, there's a lot of different trade-offs and design decisions you make for zkVMs. Right now, as you saw at the start, we've got about 20 zkVMs. Maybe 10 to 15 of these are kind of RISC-V zkVMs. That's a lot of software diversity, even if a lot of it is written in Rust, because people are writing it in different ways that may be more or less amenable to form verification. Because these zkVMs are also changing all the time, and by change, I mean that they might be going through complete rewrites on a yearly basis to some extent. Maintenance of any kind of form verification status is very hard, and the same applies to the EVM. So the EVM has new opcodes that come fairly regularly. Other kind of changes, we've got gas pricing changes that might come. EOF, that a lot of people have been complaining about on Twitter for some reason, is coming as well. And so, trying to make sure that when we do verify something and spend a lot of time and effort on verifying these things, that we can maybe automate that maintenance process, ideally just like put it into CI, is something that we're trying to experiment with and trying to work on, and obviously a big goal for us, because otherwise we'll be verifying a lot of things that will soon be out of date, and that doesn't really help anyone. And to do that, what we really need is kind of better tooling and libraries to make this much more practical. One goal for us is that we're putting a lot of money into this upfront, and the idea is essentially that by putting a lot of money upfront, we can identify the tooling that needs to be developed, we can develop it, we can set up a way to maintain that tooling, we can then show how to use that tooling to verify things, and hopefully at the end of this kind of 2-year project, we have not only verified some key artifacts, but also we've set things up so that the zkVM teams themselves understand exactly how to keep things going. But also that when they talk to a form verification team as contractors, they have a kind of set of standard tooling that they can use to make things a lot easier and faster than it is now. Now, in terms of measuring progress, so Justin Saylor wrote a blog recently where he kind of came up with these kind of stages of, stage 1A is formally verifying the soundness for the underlying PIP in the proof system, formally verifying, the polynomial commitment scheme, kind of dealing with Fiat Shamir, you've heard a lot about Fiat Shamir if you're here on day one. And then obviously kind of bundling everything together, and then obviously also verifying the implementations for the prover and the verifier, which is kind of, we're very much on board with this. And I think it's a fantastic thing that at least people who are developing zkVMs, like the Jort one in Justin Saylor's case, that everyone is thinking actively about this, and everyone has been mostly on board about how to progress and how to try and get form verification embedded into zkVMs, but also hopefully embedded into the kind of continuous development process that they go into. One thing that's quite important, obviously, for any big project is trying to find some notion of success that we want to attain and that we can evaluate ourselves against. So I think the goal for me is that the zkVMs, as a result of our effort, should be better. And that obviously means more secure, which is important and is always a key goal of form verification. But also, actually, we'd like them to be kind of more performant and more usable than they are now. Obviously, in terms of performance, I think the overhead of running something in zkVM and proving it against just running it, on your own hardware and obviously not proving anything, it's probably 100,000x, 1,000,000x. This is obviously not great. It'd be great to get improvements both from engineering and from kind of new proof systems and things like this. And obviously, everyone is working hard on this. And I'd like form verification to some extent not be something that feels like a slowdown and something that requires code freezes, but rather something that actually allows people to push a bit further, a bit faster, with a bit more confidence. And one reason for believing that this is actually kind of feasible and not just a bit of a pipe dream is that we've seen kind of form verification also be adopted kind of increasingly in industry, and AWS in particular has been doing quite a good job about this. And they've got a few blog posts now that are around that are exactly around the fact that by verifying optimizations that they couldn't possibly kind of audit, or even fuzzing might not be appropriate, they've been able to get big performance increases on kind of key parts of their stack, especially when it comes to cryptography, and therefore push performance as a result of using form verification. And by kind of better embedding form verification in their development process, they've realized that in the end, actually, they write kind of better, more efficient code. Because one nice thing about form verification is that it's one thing that helps you reason about your code to quite a high level. And a lot of times we see it now. People do find optimizations as they formally verify things. I think going back to Joel, they had a paper that will be at FC this year, where they were formalizing, some parts of the Jolt, some parts of the circuits, and they were reducing the size of some lookup tables by, I think, 87%. So you can actually get kind of good performance improvements, hopefully from form verification. And I think if people want to do, kind of crazy low-level sketchy optimizations, the best way to accommodate this is to try and set up tooling so that we can verify what they're doing along the way and help them just push things further without, the risk of them feeling like they're breaking something and not optimizing as hard as they could, or actually breaking something, which would also be obviously a bit of a disaster. So we have, there's a website set up, there's an email set up, there's a GitHub organization set up where a few of the projects are already hosted and a few more will appear soon. Everything that we're doing is obviously open source and gets open source, at some point, if not immediately. And if you'd like to get involved, obviously, like I said, we have grants, bounties. You can talk to me about it. You can go and see the website, or you can send an email to the email address that's on the screen now. I'm going to go straight into the second half of this talk, which is about zkEVM specifically, like I promised. I'll caveat this just by saying that zkEVM was meant to be presented by Quang Dao, who's a PhD student at CMU, who's been doing fantastic work on this. He unfortunately couldn't make it because of last-minute visa issues, which is unfortunately something that happens far too much. So I'll be subbing in and doing my best to give justice to the slides that he prepared. And also say that, luckily for us, right before he found out that he couldn't come, we did have a recorded version of this talk as part of a public update call that we did for the zkEVM form verification project that we're doing. And so you can find his version of the talk online on YouTube already. There's no link on the slides, but if you ask me, I can send you the link, or if you just Google, kind of zkEVM, verified zkEVM on YouTube, the channel should come up and you should be able to find it there. So like I said earlier, zkEVM is this library of proof systems in Lean. That's kind of fairly early days, but I'll talk essentially a bit about how we're trying to approach things and how we're trying to think about formalizing these proof systems, especially with respect to modularity for the proofs. So I don't need to reintroduce the project. I've just talked about it for 30 minutes. But just for context, you have somewhat of a kind of range of tasks from the back end to the implementation to the front end. And zkEVM is very much about the IAPs, which I'll be talking about now. So the goal for zkEVM is just to mechanize or formalize the security proofs of current IAP-based NOCs, and to be able to have executable implementations of these verified SNOC implementations, specifications. And I'll say, obviously, verified here means the high-level source code. We haven't started messing around with verified implementations in the sense that they go through a verified or certified compilation pipeline. Maybe that's something that we can try and do later on. So the main thing for us is that we'd like to be able to specify in proofs NOC secure, but we'd like to do this in a way that makes sense, because it's already quite hard to specify them and to prove them secure and proof resistant. So the key thing for us is to be able to have proofs that are very modular, and therefore you can compose in as nice a way as possible, so that when we do other proof systems that maybe have similar patterns in them, maybe they, a lot of proof systems end up using some check in some way or form, and you have a few patterns that come up like this, we can reuse a lot of the, past proofs that we've used and a lot of tactics, and just have a nice kind of proof structure that is repeated. And so to do this, the idea is to develop some kind of core language and to think about program logics that could be used for interactive alcohol reductions in particular. We'd like to kind of clarify some existing constructions and just kind of streamline security proofs in general. Because if you look at the literature, it's fairly clear that one, actually, the pen and paper literature has been going towards more modular proofs anyway. And it's kind of the past few years, I see you've had the split between the polynomial commitment scheme and the IOP has been kind of much clearer than it was maybe a few more years ago. And people are just getting more modular in practice, so we're not doing, I think, anything too radical. We're just trying to push this further, and we think that maybe formalizing things is a good way to kind of tidy things up where we can. Every now and then you look back and you look at some old protocols that didn't mention some check, and you realize that actually maybe it was just a some check. Or you look at something like Fry. You can look at the original paper. You can look at the Basefield paper, and there's a kind of reframing as Fry in terms of a more linear algebraic framework. And so we're looking at these things and trying to figure out what is maybe a smart way to formalize these in a way that is kind of easier to reuse and to apply to different proof systems, and also to make our lives easier, because if we want to cover a lot of proof systems, that means being able to scale up our verification effort and not just grinding out kind of hard proofs all the time, when we could be a bit smarter and save ourselves some trouble. So I'll quickly talk a bit about what an IOP-based NOC looks like in that context. this is zk proofs. A lot of people will probably be familiar. You can start with an interactive oracle proof. You've got, messages through an oracle. You have a commitment scheme. You get an interactive proof. You then apply fiat jamais, and then you get a snark, which allows you to, prove that some witness that satisfies, some relation or something like this, which can be verified with a public input. So the way that you can construct IOPs, or one way of doing this is to just do it via a series of interactive oracle reductions. So you can take, your intended IOP, and you can kind of reframe this in terms of a series of interactive oracle reductions, which are just intermediary steps between what you start with and what you actually want to end up with. So we're already seeing a bit of, kind of modularity come up in some sense here, and I'm going to push this a bit further. So let's take the subject protocol as an example, and let's take a very simplified version of a subject protocol as an example, where you just got a bivariate polynomial. And you've got this relation, maybe let's call it an input relation here, which is obviously what you start with, which is just, sum of the polynomial over all the values of the variables equals to, t. And at the end of the subject protocol, you're going to get, some relation, which is based on challenges R1 and R2, equals to something else. So we've got kind of two rounds here of the prover sending something to the verifier sending back a challenge, and then at the end, you get the intended result. If you're not familiar with subject protocol, I'll say nothing that I'm going to say kind of depends too much on exactly how the subject protocol works itself. It's just trying to illustrate how we're trying to break things down in as modular a way as possible. And in particular, I want to try to get a bit of a link to kind of program logics, to try to reframe IORs into program logics and to see how we can get nice composition rules based off of that. So back to our subject protocol diagram here. If we just zoom in on the first round of the prover sending, S1, and the verifier sending back a random challenge R1, you start with your polynomial. You obviously kind of fix one of the variables, so you get this polynomial S1 here. And then compared to what I had earlier, what I've done here is just introduce this kind of middle relation. So that would be kind of some intermediate reduction of knowledge. You'll see here that this is still just a bunch of polynomials, but from that you can kind of go even further. And if you zoom in on the part that's highlighted here in the kind of yellow box, you can split this up even more, and you can have some kind of R mid prime relation here. And the nice thing here is that by kind of breaking things down as much as possible, you've ended up with S1 here, which is just P of x and then 0, and P in x and 1. And for the verifier to check this is deterministic. So there's kind of, the probability of that failing is 0, which is all great. And then you end up with, your kind of mid-prime intermediate relation here. And the property of that is just going to be d over the size of the field. This is just a Schwarzschild lemma, which comes up if you try to prove, the soundness of the subject protocol as usual. But the nice thing here is that by kind of isolating things that have property 0 failing and just recovering, the one thing that actually has some non-zero probability of failing with the kind of normal bound that comes from Schwarzschild lemma, you can get round-by-round guarantees essentially for free. And this is quite attractive, right? Because you can think of, if you start instantiating other protocols in a similar manner, you can probably do the same thing again, and you can start to reuse tactics, and you can start to sub in different components of proofs for parts of protocols that kind of look like each other. And at the end, this is the kind of R-mid relationship here, which was right here as well. So you're not kind of changing the protocol or anything, you're just breaking this thing down as much as possible. You can push it even a bit further if you want, and just kind of simplify things a bit further if you want. And you can define this kind of virtual polynomial here, P1x, which is just kind of what it was on the past slide, but slightly written in terms of one polynomial. And we can call these virtual polynomials. You can kind of call them something else if you like. But essentially, we're just trying to simplify things as much as possible, so that when we look at a single message going over as part of the protocol, we can then just have small proofs about this and compose things from this. And what we're trying to get to here is some connection to kind of Hoare-style program verification. So in Hoare-style program verification, you've got this notion of Hoare triples, where you've got, given a program C, you might have, you execute it with some precondition P, and you get to some postcondition Q. And this is what a lot of program verification is based on. You get these nice kind of rules to kind of deal with these logics, and we'd like to get something maybe similar in terms of reductions. So you would have, some reduction PV for the proof of verifier, and when you execute that reduction on something satisfying R1, you would then get something that satisfies R2 and be able to reason about this with some appropriate logic that would apply to interactive Oracle reductions. So this is somewhat, I think, our goal here, or certainly the goal that Kwong has been pushing, which I think seems very promising. And like I said, we have now, kind of very basic one-round sum check proofs that's kind of passed completely, and we'll be expanding that to kind of more complicated examples, but hopefully doing things in a normal way will mean that the more complicated examples don't become that much more complicated. So I'll talk a bit, just to finish up on the current state of zkEVM. So currently, as I said, we've got some definitions of interactive Oracle reductions. We've also been working on a kind of competition-friendly polynomial data type in Lean. This would be something that basically just kind of can actually run in some reasonable amount of time, and then developing an isomorphism between that polynomial data type and the polynomial type that's used in MassLib to do all the proofs that we rely on. And like I said, we've got kind of a specification and a proofs of security for a single round of sum check, and we'll be kind of expanding on that to obviously multiple rounds of sum check with round by round knowledge soundness, and then into bigger IOPs. So we're very interested in kind of pushing composition of IORs and having nice proofs that they preserve security. So this just goes back to what I was saying about modularity and thinking about composition. And like I said, I think in the first part of my talk, we're working towards having executable specs that are directly tied to security proofs, and so we'll be doing this for the Spartan IOP, and then we've also got blueprints starting very soon for Fry, Stir, and Were. So Fry will be with the help of Nethermind, and Stir and Were will be with the help of least authority. Once we have these blueprints set up, one thing that we're also intending to do is to set bounties for specific theorems. One nice thing about Lean, or doing things in a proof instance in general, is that obviously it checks proofs for you. And so blueprints, for context, are just a dependency graph of theorem statements that need to be proven to get to a final result. Anyone should be able to look at the blueprint, look at a theorem statement that needs to be proven. Some of these might be quite simple. In particular, some of these might just be things about Reed-Solomon codes that shouldn't be too complicated. And anyone can then jump in, do a pull request, submit a valid proof, get a bounty that's been fixed ahead of time for completing that proof. And this should hopefully allow us to kind of parallelize proving efforts, get more people involved, have a lot of tasks from very easy to very hard. And if anyone wants to prove the proximity gaps conjecture in Lean and save me the trouble of having to figure out that their proof is correct, we will be stating it in Lean, and you can just submit a proof request, and we'll see what the Lean type checker has to say about it. And similarly for other conjectures, right? We've got some longer-term goals, obviously, past these kind of short-term plan work. This is just kind of formalizing the compilation steps once we want to get to a complete proof system. Kind of basic notions like rewinding of knowledge soundness and zero knowledge that are kind of traditionally quite hard to formalize anyway. We'll see what progress we make on that, but obviously we'll get there in the end. And also obviously trying to improve performance. So this is either matching our executable specifications to Rust implementations that are actually faster than people use in production, but also potentially seeing how far we can push code generation from Lean. And ideally, it would be nice to get executable specs that execute at least fast enough for differential fuzzing, if not to be run in production. We'll be producing some tutorials and basically onboarding material for zkEVM. To try and get as many people involved as possible. It's a open source library like any other, and if anyone has followed what's happening in Lean with things like MassLib, it does seem like there's a lot of potential to build up kind of these nice comprehensive libraries without also kind of breaking them down into a horrible mess. And it would be fantastic if this could be a nice contribution, not just in terms of form verification, but because we're thinking a lot about kind of streamlining proofs and clarifying some proofs. And Kwong in particular is a kind of genuine cryptographer before being, a lean or form verification person, and we're hopefully kind of aiming to have, some contribution back that flows back into cryptography and have a bit of a feedback loop between both, and to not just be formalizing things for the sake of it. And in particular, the audience for this library, we're not thinking of just form verification people. We're trying to make this as usable as possible for day-to-day cryptographers. Some cryptographers obviously already write reference implementations, some don't, but we're working quite hard to make sure that things that you just kind of use out of the box, like fiat jamais, like other cryptographic gadgets, are usable in the same way in Lean, usable in a simple way, so that what you're left with is proving the information theoretic part of your IP as part of the proof system, and the truly kind of new parts of whatever new proof system you've come up with, rather than wrestling with trying to put in some kind of bastardized, formalized version of fiat jamais in there. And it would be fantastic, obviously, if anyone wants to try it, give us feedback about what would make it more usable, and kind of, maybe think and experiment with trying to, kind of use this library kind of, to formalize their proofs, or to just have a look at what it would mean for them to formalize their proofs and what kind of challenge that would entail. Obviously, on the mathematics side with MathLab, there's a lot of kind of big, now mainstream mathematics projects going on, which has been very exciting. Some people have managed to formalize entire papers before peer review finishes. Peer review for them sometimes takes a bit longer than it does for us because they kind of journals more than conferences. But it would be very nice if we can kind of get things to a point where adding a new proof system that comes out in a paper or a preprint on ePrint doesn't take too long and becomes a very tractable task that can produce kind of nice reference implementations for people to then base kind of actual implementations that will run in production off of, and maybe kind of differentially fuzz and formally verify against down the line. So just as a quick summary, and just reiterating a few things, I think everyone here will probably agree that formally verifying snarks is important. We all know the risks of things blowing up, and we're trying to kind of help in that direction with zkEVM in particular for IOP-based snarks, following the kind of key ideas of reductions as the main building block, and trying to make a connection with program logics and program verification ideas that will hopefully help us kind of get nice composition theorems and to kind of make this a lot easier and manageable. That's it from me. Obviously, thanks for bearing with a double talk and the rambling that goes with it. I think we might have a bit of time for questions. And so, yeah, any questions, I'm happy to answer.
First of all, thank you so much, Alex Hicks, for this talk. It was a double talk, but it was like fascinating and went over all the explanations very clearly. Raise your hand if you have a question. All the people with, no, just so I know how many questions. All right, go ahead.
Okay, so I'm going to be one of these people at a conference who, instead of a question, I'm going to make some observations. Sorry. So it's a great, those were great talks, and thanks to the other presenter who couldn't be here. So what I got out of it was that there are some simplification strategies that we can use, and I've written down 4 of them. The first is to focus on sort of fewer alternatives that people have already congregated around. So Rust, RISC-V, Lean, MLIR, and so on, but not proof systems, because the most obvious thing is that you have to standardize on proof systems, but they're changing too fast. And actually, there are enough commonalities between proof systems and what they're doing that we don't need to fix those, and various projects will have different trade-offs that require use of different proof systems. The second is, if we write directly in proof-assistant languages, like Lean, with macro systems that support embedded DSLs, then that means that we're not having to freeze code in order to verify it. That is directly the language that we're writing it. If it's expressive enough, then we don't necessarily need to write in a conventional programming language like Rust, because we can extract to that, or we can have the DSL compiled directly to something efficient. Then the third thing is, So lookups, people sometimes think of lookups as functions. I would encourage everyone to think of them as relations because that supports non-determinism. And you can also think of a polynomial gate as a relation. So basically all you have is a bag of variables and sort of relational constraints between the variables. And essentially everything in a circuit can be expressed like that. Except that, so sometimes you use the technique where so you constrain part of a circuit, and then with those variables committed to, you extract another challenge using Fiat-Shamir, and then the rest of the circuit can be dependent on that challenge. And that's very often gives asymptotic improvements. But if you think about it, a protocol is the same thing. So we have this isomorphism between circuits and protocols. It seems to me that if we can put those in the same model and use because this sequentiality, so the adversary does not know the challenge until a certain point, is why you need sequential logics rather than just a purely relational logic. So yeah, if we can view circuits and protocols as essentially the same kind of thing, that potentially makes it easier to do end-to-end verification of a system of circuits and protocols. Okay.
Thanks, Dara. Now a real question.
Yeah, so I got the impression from the presentation here that a lot of the verification efforts are very, very focused on completeness and soundness, and I saw only passing mention to zero knowledge.
Most zkEVMs on zero knowledge at the moment. The zk is a lie.
This is fair. I guess I'm wondering where you see it fitting into the long-term roadmap here of, down the road having actual zk, in an ecosystem like Ethereum that is verifiable through a framework like this.
Yeah, so I think, so kind of like I said here, we are interested in like mechanizing these notions, zero knowledge as well. We'll get to that. I think obviously we'll try to get to that at least maybe before, zkEVMs truly become zk. And I think what will enable that is just kind of better performance, because at the moment you can't really do client-side proving, and so if you're sending your witness over to a server anyway, it's not much point in calling it zk. But yeah, it would be nice to get to that. It would be very exciting to have kind of actual zk on Ethereum. It'll be a bit of time, and some of it will not just depend on me, so I don't want to commit other people to timelines. But we'll get there. But not with zkEVMs. Oh. Then problem solved.
Thanks for a nice talk. You mentioned security proofs, so are you doing them in the symbolic model or the computational model, or is it something different?
It's one of these things that we end up talking about and then not no kind of final opinion on it. At the moment, it's maybe a bit more computational, but I don't want to kind of commit Kong and the others to something right now.
But it's no general game hopping technique, or?
Not at the moment. I think maybe once we have a few more things fully fleshed out, we'll think about how to refine that. But nothing set in stone at the moment.
Thanks.
Hi. You spoke about using Lean to actually sort of compile from Lean directly to something else, right? So I guess you're using Lean as a functional language in that respect, regardless of its proofing abilities. Did you consider Haskell? Are you considering Haskell?
I can't say that we did. I would say that none of us are Haskellists. That would be the one big reason. But also the ability to kind of co-locate your proofs directly with your code is quite attractive. Presumably, I suppose that if we did everything in Haskell, maybe we'd prove things in Agda or something else. But yeah, no Haskell involvement so far. Sorry.
So translating from dependent types to Haskell is, I mean, has been available in Rock for ages, so, and you can do the same thing for Lean.
More questions?
You mentioned you'd only done one step of sum check, but then why wouldn't it work for, I mean, the entire, what does it mean by one step, and why wouldn't it work?
I mean, it should probably work for more rounds.
Okay.
It's just that we had a lot of fixing to do with respect to the underlying Oracle library and getting a bunch of sim lemmers to basically like deal with the entire kind of messaging part, to just leave out, you know, the information theoretic part of the proof to fill in manually. That took a lot of work. Now that's fixed, we can start adding more rounds and reuse that. Yeah, I don't, like, it shouldn't be kind of too challenging.
The whole goal of what your slide said was to do these mini reductions, and the second one is exactly the same as the first one, right?
Yeah, so that's why it should follow. But when I say like we just did sum check, I mean like the commit was like a week ago.
Oh, okay, I see, okay. All right, thanks.
I have a question related to like the first part of the talk, when you were talking about the requirement that you want to check from the polynomial commitment scheme, and you were saying any kind of security from standard cryptographic assumption to idealized model. Like how, from the point of view of industry, is seen, because there is, at least from the theoretician point of view, we know that there is a big difference between having a proof from a simple assumption and on the other side having a proof from idealized model and anything in between, particularly because the more you move towards idealized model, the harder it is to formalize it or to verify it. How this is seen from the point of view of industry?
Like how hard is it to formalize?
How hard it is to formalize, how different it is in the term of how different it is in terms of how do you believe in the proof? Would you also implement the scheme regardless? Like, what is the point from us to try to make good proof if industry see all the proof at the same level, or does it actually see all the proof at the same level? I know it's a very general question, but I don't get any answer when I try to make this question, so I try every time. Maybe someday I will get an answer, I don't know.
So I mean, I'd say that we try to prove things at the same level as they appear on paper. We're obviously not trying to add any kind of assumptions or to tweak any kind of security model. That would be my short answer. My long answer would be when we try to prove something big, we'll see what happens there. But you know, the plan is to not kind of compromise, and for any compromise, obviously, to at least kind of document it, you know, very explicitly. We'll see. Ask me in 6 months, and we'll have something bigger to discuss and see how we've done.
Okay, thank you very much, Alex.